All right. Cool. All right, then I would say let's get started. Welcome, everybody. Thanks for coming back or for joining the fourth iteration now of our CMFI Mass Spec seminar series. So yeah, today we're gonna get a little bit into practical aspects of LC-MS data acquisition, and then also we prepared like a little hands-on exercise today to get started with our data analysis. So yeah, the first thing will be upload and data sharing. Now, yeah, we're gonna start with again some basics again about the seminar series. So in case this is your first time, so yeah, we want to like cover different aspects of mass spec hardware and particularly data analysis approaches. It's open to everybody, so yeah, feel free to invite your colleagues and friends. Just like you need to sign up here. Ideally, so I email around the Zoom link typically for every Tuesday. Also, one important change for like next week and probably also like the following weeks is that we will move the seminar to the later afternoon because we have different guest speakers from the US, and yeah, due to time differences, our afternoons are gonna work better for them. So yeah, pretty happy and very much looking forward to have them. Yeah, it's gonna be fun. Yeah, so next time will be like the 15th of February. Peter Dorstein will give an introduction and some hands-on exercise on molecular networking there, and yeah, I hope you're all excited about this too. And then the following week, Ming, or the following 2 weeks, Ming will present some other new tools, and then we will move on with feature-based molecular networking. But yeah, to do all of this, obviously, we first need some data to actually analyze. So yeah, our goal of the class today, mute yourself, please. Thanks. So yeah, like the goal of today's seminar is to like actually look at the instrument and like acquire some data. Okay, so and then yeah, convert this and upload it to publicly share this particular file or the particular test files which I shared with you in my email yesterday. Perhaps somebody could post that link also in the chat if somebody did not manage to download it yet or did not get that email, so they still have a chance to download the 3 raw files which we will need later. And ideally you also installed the ProteoWizard package that contains MS Convert, which we will need. Perhaps somebody could share that link in the chat too. That would be nice. All right, but yeah, just like a little recap what we talked about so far. So yeah, like in the last lectures, we talked about the basics of mass spectrometry, and in particular liquid chromatography coupled to mass spectrometry, as here illustrated in this LC-MS setup with like a Q Orbitrap or Q Exactive instrument. And we also talked about a little bit the different scan modes we can do. So like here, for example, like just the full scan where we like just measure basically like the intact masses of molecules, but then also how we can like use the same type of instrument to isolate precursors and fragment them and create MS spectra. So, and this is kind of like the data what we actually need for like the downstream data analysis in the next couple of lectures. So yeah, I showed you that the type of like MS experiment we typically do in that context are like product ion scans, where we kind of like set our first mass spec here, in this case like a quadrupole, for example, to a fixed MZ value, then fragment the isolated ions, and then get like a scan readout of like the fragments. And yeah, in the animated version, this looked like this. So just as a little recap, so we get here an isolation in MS1, then fragmentation in the collision cell, and then yeah, like a scan of like the fragment ions. And yeah, just here as an example, here this famous natural product would produce like here this like molecular ion at 821, And then if we isolate this and fragment this, we get like this product ion spectrum, right? So these are like important terminology for like downstream in this class. So now the question, of course, is how do we know in a non-targeted experiments to which masses we're going to set that quadrupole to isolate precursors for the like consecutive MS scans, right? And here a very important method we use is data dependent acquisition, or short DDA. And I think for like most of like the molecular networking applications, for example, this is the type of like data what we get. And what happens in DDA is that we iterate between full scans or MS1 scans, which we also call survey scan. And then the machine automatically picks the most abundant ions in that survey scan to then submit them to consecutive MS events. And what is kind of like illustrated here already as a circle, is this iterative process that rolls through like our entire LC separation and through our entire analysis. And here another important term is that we call one round, so basically one MS1 event plus the consecutive MS2s, a duty cycle. And this duty cycle, and especially the length of such a duty cycle, has some important implications, for example, for like the number of MS1 data points we get for like chromatogram building, but also for like simply like the number of MS2 events. And then, you have to like find a balance between like different settings there. And to just give you an idea, so typically this happens really fast. So like one duty cycle normally is around like a second or so, and you get like really like a lot of MS and MS1 information, so typically like thousands of spectra per LCMS run. And fortunately, Paolo in our lab just gave like a little presentation this morning already where he discussed like different like DDA settings, and I just stole the slide from him. And I really want to like spend now 10 minutes or so to go to each and every one of them, because I think like all of those settings are kind of like fundamental for setting up a proper DDA method and to get like really like good data for which you also like then eventually gonna get good like molecular networks downstream. But if some of those settings here are not like set appropriate, then your entire analysis can go like downstream pretty quick. Okay, so now, we're gonna go through this really quick, and if you have questions, please ask. So I really want to spend like some time to make this, as clear as possible. All right, so let's start with like the first one. So here, what we typically call top N is kind of like the number of MS2 events you will have after each MS1 event in such a duty cycle. Okay, so here if we think about our MS1 survey scan here on the bottom left, then it would be simply the number, and let me actually indicate this here. So this would be, for example, for top 3, it would pick like here the 3 most abundant ions, and then each of them gets submitted for a consecutive MS2 scan down here, okay? And then if we would have top 4, then it would be like 4, right? And if we had top 15, which was like more modern machines now is like kind of like standard thing as well, then it would be 15. So this has, again, important implications for the length, obviously, of each duty cycle. All right, then let's go see to the next one. Okay, this is monoisotopic precursor selection. So for metabolomics, this is not super critical, as most often, if we look at like an MS1 event, our monoisotopic peak is also the most abundant peak. But if we have like, for example, some, I don't know, halogenated compounds or especially higher mass peptides, right, then often the most abundant peak is not the monoisotopic peak anymore, but rather here like the plus 13C, also like isotope look. So here it can be important that we actually like pick the monoisotopic peak, particularly for peptide analysis. And there's like, yeah, simply a setting that basically tries to pick then indeed here this first one and not simply like the most abundant one. Okay. Then the next one would be the isolation width. So this is simply the window size in which here each precursor gets isolated. So, okay, maybe let's, yeah, illustrate this also here. So again, if we would have like 3 MZ or so as an isolation window, then typically like the isotopologues would be isolated as well. And if we make it more narrow, then eventually only the monoisotopic peak here would be isolated. This especially for like environmental samples and very complex samples can be quite important. And that's also like a little of like the tiny differences between some commercial QTOF platforms and, for example, like the QOrbitReps, where yeah, like the performance of the quadrupole actually differs quite a lot. And you can, with like the Q-exactive, for example, like isolate with like 1 MZ, like easily, but like with the program access, for example, that does not work very well. So there you need to have like bigger isolation windows. All right. In the same realm, there is the isotopic exclusion, which basically simply tries to avoid the picking of like isotopologues as DDA scans. So because if you already picked like the most abundant one, right, like the one with 0, 13 Cs, then you already have MS information from this particular ion species, and getting like additional MS scans from like the isotopologues is kind of like a waste of scans. So you don't really like want that normally. Then also what you don't want, as you like move on with your duty cycles, you don't wanna like perform MS of the same mass over and over again. And I think this is a very common mistake you find like in some public data set, that people like don't like use this option, and then they basically waste a lot of scans to just like perform MS from like the same molecule over and over again. So very classic is if you have a log mass, for example, and there's a constant signal, and you see like every duty cycle one scan goes like for like the your internal calibrant in that case, and you're wasting kind of like a lot of like scan time of your machine, and hence less molecules you potentially can analyze. All right, then apex trigger. This is kind of like a very nice feature with like the Q-exactives, which I really do appreciate that Thermo has this here. Not every MS vendor has such a setting. So this is kind of like optional, but I think is a really smart thing, because especially if you use dynamic exclusion, what will happen if you like look here, for example, at a chromatogram where you would have a peak like this, right? Okay, so this is here retention time, and here intensity. Then what happens is, as soon as like this peak comes up, an MS event is triggered and then put on the exclusion list, and then eventually not be considered again till like the exclusion list expires, typically after 10 seconds. So then you would get your next MS event here after yeah, just like basically like the most amount of like the compounds is gone, right? So wouldn't it be smarter to actually wait with that trigger and trigger it exactly like at the apex of the peak? And yeah, basically this function here in the Q-exactive, for example, yeah, like tries to yeah, like monitor like the slope of a precursor signal, and then once it kind of like goes to 0 or like decreases again, then trigger like the first MS event. And I think we have like particularly good experience with like optimizing those settings to get higher quality MS with higher signal to noise. All right, then coming to like some more general settings here, we can like choose the resolution of the mass spec. So in particular with Orbitrap analyzers, this is directly coupled to like the actual like transient time. So the higher your resolution, the longer you need like to cycle your ions inside of your Orbitrap, and hence the slower the machine scans. So here it's a question of finding like a balance, yeah, to get fast scan speed, but also to get like high enough resolution. In particular, if you like work with like environmental samples and mixed, strongly like mixed compounds, then might be important to get like higher resolution. Okay, Efi, shall I just quickly finish the last three things and then we can like discuss questions? I see this was a hand. Okay, all right, then now coming to like the micro scans. This is basically the number of like raw scans are performed in an Orbitrap, which are then basically merged to one scan, which would be written into like the data file. And here, like our default is typically 1, but for example, when you work with like proteins or so, then people like really like to like increase like the number of microscans, which basically sums up signal and then increases like signal to noise. Obviously, the more microscans you do, also like the longer the machine takes to like acquire like one actual scan then, and hence your duty cycle like increases and you get less spectra. Okay, and then probably like the most simple one of all of those, NCE, this is normalized collision energy. So this is basically a value in percentage of like the energy we apply to activate like the molecules in our collision cell here to basically fragment them for MSMS. And then another thing that is very typical for ion trap based instruments, so both like LTQs or Orbitraps, but not for TOFs, for example. So you won't find that there, is the automated gain control. And the automated gain control is actually a really neat setting that kind of like measures the number of ions that are submitted to an Orbitrap readout. And what that aims to is basically to reduce space charge effects. So you may remember that little like window experiment I stole from like The Simpsons, where like all like that ions try to like pass through like that like little window and then they get stuck. And you kind of like have similar effects inside of like an Orbitrap when you get too much like ion density. So then you can actually like see like an effect that like the different ions expel each other, and what that typically like leads to is like peak broadening. So yeah, here AGC, it's kind of like a balance between like dynamic range. So obviously you want to like let in like a lot of ions so that you like see like the widest like dynamic range, but then you don't want to like let in like too much, so you get like more narrow peaks and higher mass accuracy. All right, this was the DDA setting rundown. Fortunately, this will be going to YouTube later, so yeah, you can also like hopefully revisit some of them or ask a question now if something came to your mind and you want to double check. Efi, I think you had one.
I have 3 questions actually. So I'll just go with the fast one. So the apex trigger, you said that this is something that is very, you run into it first time in the thermal Orbitrap, but which one did you say?
So it's, well, I think it's with the newer tribrids and like the newer top of the line instruments, they probably have it as well. But yeah, I first like used it with the Q Exactive. So in the LTQ Orbitrap we had before, for example, this was not available. And yeah, I think this really like, I found it quite nice when I first saw this. I said, oh yeah, that makes sense. Because yeah, like the problem with the exclusion list, that you kind of like get your first MSMS not at the ideal moment, but yet, you know, rather like here at the beginning of the peak, and then kind of like miss actually like the best opportunity when like the chromatographic peak is at the top. Yeah, that's like a common thing. So that's why typically we made the exclusion duration relatively short. But yeah, like with the apex trigger, you can actually keep it like a little bit longer, and hence also, you know, just like get more MSMS scans. And yeah, I think for non-targeted metabolomics and really MSMS based stuff where you want to like go as deep as possible, like really like that number of MSMS scans and not wasting them, but only get like them like placed at the right time. This is really important to get like more coverage.
Yeah, because I mean I noticed also quite a few times at my chromatographic peaks that I don't get the acquisition at the top one, which was really weird to me. But yeah, good to know. And we have an IDX, so I don't know if we have that.
I think you should probably have that there. And the
Okay.
settings are relatively simple, so it does not say too much about its actual like algorithm, so how it like defines like the apex. I think you can just like define like the minimum and maximum wait time, which kind of like corresponds a little bit to like the peak width you expect.
Okay. Okay, then I'll just ask in the end the rest. No problem.
All right, cool. Yeah, I think especially to those of you who have like a mass spec available, or who are like here in Tübingen and want to like stop by, I think it's really nice to go actually to the instrument and like start playing around with these settings, and then yeah, like get like a little bit more a feel on it. So yeah, like unfortunately this is a virtual seminar. Otherwise we could now all walk over like we did with Raphael and Paolo a couple of weeks ago, and actually go to our instrument, right? And kind of like the rest of the, well, not the rest, but like probably like the next 10 minutes or so, what I want to do is I want to like remote connect to actually our instrument and like, yeah, just like analyze a sample with you and play a little bit around with those settings I just presented, so you kind of like get like a little yeah, feel for how it looks like. Actually, most of the time in the lab you spend in front of the computer anyway, so like, I mean, yeah, so it's probably not too bad to do that here over Zoom together. And yeah, before I connect, I just want to like highlight 3 tools I'm going to use then when operating the machine. So for yeah, like the Thermo Q Exactive in our case, this is typically here like the tune, which is like the basic instrument control for the mass spec. So here, yeah, as the name says, we can theoretically tune it and calibrate it, do some like yeah, basic daily operations, like putting it in standby and activating it again. But also we can get like some diagnostic readouts that tell us like whether the mass spec is actually performing well. So then for the actual analysis, so when we want to submit samples, we use another software called like Excalibur. So this is basically like the sequence manager. So here we list like all the samples we want to run, and also like define the actual settings, both for the mass spec as well as for like the liquid chromatography. And then one that is like, well, maybe not that essential, but at the end we spend also a lot of time with is the qual browser. That's basically like the yeah, I think now antique software from Thermo to like analyze MS data. Now I think there's Freestyle as well as an alternative. I still like qual browser better, so I try to like use it as long as it's available. But yeah, so now let me just get out of this here really quick and connect to our remote machine. I hope you can still see my shared screen. Maybe I can get like a confirmation from somebody.
Yes, we can see it.
Awesome. So yeah, welcome to our mass spec. So here I basically opened up now the tune page, and well, maybe it's a little overwhelming at the beginning, but like the most important thing is like the live spectrum view in the middle. And right now you can only see that there is a static spectrum. And this is perfectly right because the machine is still in standby. So in order that it starts scanning, I have to go here like to the top left and then turn the instrument settings to on. And now what we should see is that there is like something moving. And yeah, this is generally what we call, oh yeah, nice, we see ions, because yeah, we get some signal. So now obviously this is like very much at the like, yeah, like lower end of intensity. So we have very long injection times in order that the machine acquires enough or accumulates enough ions to be submitted for an Orbitrap scan. But now if I would change here this valve and start actually infusing some solvent from like that comes down from our pump, then here like the signal should typically become more stable. And then, yeah, like now I get like shorter injection times and better signal to noise values. So then also I have like this traffic light here at the top. Everything is green. So this is nice. So it means that like, yeah, like the vacuum and the electronics are like all okay. And also that it was recently calibrated. If it's like out of calibration, this typically becomes yellow and tells you, hey, you need to like calibrate something. So now, okay, let's go to Excalibur. So this is the second software with which we actually gonna now analyze one of like the samples. And here is an example today. I just want to run quickly our QC mix. And this is here like the second sample in like this little sequence I already wrote. And what's very important here, you can see that I defined the file name here as QCmix_1. And then I defined also like a path where this should be saved. And then I defined a method here. So this basically has like all like the settings, and I will go there in detail in a second. And then also very important, I define here the position. So where in the autosampler like the vial stands. And then also here on the very right, the injection volume. So here for our QC mix, we're going to inject typically like 2 microliters. And yeah, just to give you some background, this is a mixture of 6 antibiotics, sulfonamides, as well as like a coumarin derivative. And if I want to like start this, all I need to do is I need to basically highlight here like the row I want to start, and then press this run sample button at the top. And I click this, and then it asks me here a couple of things, whether to put the machine in standby afterwards. And I want to do that, and that becomes very important if you run the machine with like hundreds of samples overnight, and then eventually you want that it just like stops after your analysis is done and goes in standby, particularly at the weekend or so. This is really important. Okay, and then it also asked me if I want to save changes here in like that sequence I wrote. And yeah, we can just do that. So basically all changes are like saved in like the actual sequence. And then now on the left here in the acquisition queue, you can see that there is now sequence row 2 basically listed as a sample. And then now in theory, like the tune should exactly halt. So it's now here says in general instrument state that little like Excalibur symbol. So that means the tune is now controlled by Excalibur and is waiting for the LC to inject the actual sample. And then after a couple of seconds or so, once like the machine is basically ready, it has the right pressure, and so we should see that the analysis starts. Can like check also here the status, and then we will see, okay, here Thermo Scientific S2 like is basically preparing for run. All right, and while we wait for run, I just want to show you quickly how like such a method file here looks. So I already selected that one, so this is like all set. But if we would start from scratch now, we could edit this and actually like go through like some of the settings and make changes here. And here I really would encourage you to like think about like those settings I explained a couple of minutes ago, because basically all of those settings we will find now also here in this editor. And then first of all, we have here like our HPLC system where we can like define like a gradient. So we use like acetylnitrile water as mobile phase and run like this like 2-step gradient. But yeah, I think this is very much like standard. But the exciting part is down here when I click on like this Exactive HF logo on the left, then I come like to the mass spec settings. And now, if I maximize this, you can see I selected here like this full MS, DD MS2, so data dependent, top N MS scan. And this is also like a segment that goes over like the full method length. So here we have like a total of like 18 minutes method length, and then it basically does its spiel over and over again and goes through like this different DDA duty cycles. And now, here on the right, what you can see is actually that there is a couple of settings. So the most important ones I mentioned before, such as here resolution for MS1. So this would be full MS. Then the HEC target. Then a maximum injection time. So this is kind of coupled to the HEC target. So basically the maximum time it waits to like reach that level. Then the scan range, which, yeah, we did not mention before, but I think this is very intuitive. So this is basically just like the mass range in which you're scanning, and obviously like depends a little bit on what kind of like molecules are looking to. And then the same resolution setting here for like MS2, also an HEC target, and the maximum injection time. And then there's this loop count here, which basically is the number of precursors from each survey scans that are submitted to consecutive MS events. So if I would increase this here to 10, then you would see that here my top N also says now 10, right? So if I change this, then now I would get more MS scans. Then the isolation window, as I showed you before, okay, this is 1 MZ, which is kind of like the default for us. And then directly under it, there's like this CE, collision energy, and in our case, we use here like a stepped collision energy, so it actually does 3 different activations at different normalized collision energy. So this is also something that is perhaps not available to like all different mass specs, but yeah, with the Q-Exactive series, this is a very nice feature. And then yeah, there's some other like isotope exclusion settings here, a minimum threshold, and then yeah, here like that apex trigger I mentioned before. So we look for like the apex between 2 and 15 seconds of like the first occurrence. And then yeah, there's some isotope exclusion down here, and then like our dynamic exclusion lengths with 5 seconds, which is rather short. So like depending on your chromatography, you can also make this longer. All right, so now you get like a brief overview of the settings. Yeah, if I close this, it asks me if it should save any of the changes. I didn't do any, so we don't really need to do that. And now, yeah, going back here to my Excalibur software main page, I can see in the status here on the left that actually the machine started running now. So this is really cool because, okay, it seems like to work. And if I yeah, look here at the acquisition query, it's green. And now I can also change from like the sequence view here, what I have on the top left, to actually the real-time plot. And then we can see already how the machine is acquiring data. And okay, here at the top, you see basically like the chromatogram summed up to like a total ion chromatogram, kind of like slowly like now, yeah, grows now over time. And at the bottom here, let me make that a little bigger. You can see like the MS and MS scans that are performed right now. And as you can see here, there is some full MS, and sometimes there might be also an MS1 event, which we can, I think, not see very well here in Excalibur because it just shows you every second or every third scan or so. But if we would go to tune, it actually shows you all the scans it performs, and you see already, okay, wow, this is much faster. And here you can see, if you, I hope Zoom captures this with the right frequency of the screen update. But yeah, basically like iterates between like this MS1 and MS2 events. And yes, I said this is happening really fast. So we get like, yeah, a duty cycle of 1 second or so, and yeah, like a ton of MS2s per LCMS run here. So yeah, I was just hoping to see when like the first peak eludes, so you kind of like see how like this entire thing here changes. So right now we basically just have are still like at the baseline level, but at like a certain retention time when one of like the hopefully standards will elute down from our column, we should see a nice peak. Probably don't want to like wait too long, so instead what I'm gonna do is I'm gonna open our qual browser to actually quickly like open a file I run already like earlier today, and therefore I can here just like browse into like the data path I defined, and then see from my yeah, like files here that there's a QC, and yeah, here nicely we can see that we have some, yeah, nicely shaped peaks, And now if I would click in them, I could like see like the mass. Right now, there's no MS2 information displayed. This has something to do with that I put a scan filter in here, which I can remove here through this ranges. Remove the scan filter. And yeah, now it looks like this black spiky thing here, because if we zoom in, then you will see, yeah, that those are like a lot of like spikes. And this has something to do that like the signal intensity from like the MS1 scans are at a different level than the signal intensity of the MS2s. But if I would click now somewhere here, I could actually see, okay, here full MS, there's the, there's the mass 279. And then if I move on with like the cursor, then I should see, okay, here's some consecutive MS events. So now one important question you may wonder is, how can you do now the same thing and visualize the files I just shared with you through like the Google Drive link? And yeah, like the bad news is that I cannot share Excalibur and Qual browser with you, because obviously we need like a software license for that. So this is not open access, and you could basically not really like visualize the data we just acquired and the data I shared with you. Now, the good news is that there's a ton of different like open source tools that allow you to like view and analyze mass spec data. The only thing is that you need to like put those files into like the right format. And now, yeah, for like the last 10 minutes or so of today's class, we want to like quickly convert these raw files I shared with you, and then upload them to Massive and make them like publicly available to like the community, but also for us to use them in combination with some of the GMPS cloud-based tools. All right, so to do that, I'm gonna quickly go back here to our machine. Okay, now we also see in the meantime, our standards started to elute, so that looks good. But what I wanna actually do is here, go to like this test folder where I have here like this 3 raw files downloaded. And yeah, just should I give you all a minute or so to find those files on your computer? So did everybody download this, or was there some problems? Okay, can I get thumbs up? Okay, Alejandra, awesome, you got it. If not, yeah, I'm just gonna move on now, but you can then try it like later on your own if you can't like if you don't have them available right now. Okay, so because yeah, converting them to MZML format is quite simple if you have Proteo Wizard and MS Convert installed. So like all I need to do here is basically right click and then say open with MS Convert GUI, and then it basically opens here like this little software tool where I can first of all select here like the files on the left, and if I would click on browse, I can probably select the other two. So now I should have all 3 replicates here. Then I can define an output folder here in the output directory. So probably gonna call this MZML or so. And then one thing that is really important, there's like this different filters here. I can add it now in my presettings, which I saved. I already have that included. But in order to use GMPS or other like feature finding tools, what you need to do is you need to convert your profile data to Centroid. And therefore, I use here like this peak picking filter, and then have this here set as vendor algorithm, and importantly for both MS level 1 and 2. And now, yeah, if this is like all set, then you can always go back to that view I have and reproduce that. So that should work pretty well for thermo data. Then you just need to like click here start, and then it asks me if it should create like this new directory, what I just defined. And then here it does now some calculation and writing of new files. And then, yeah, quite fast. When it says finished, I can close this. And now here in my test data folder, there should be this new folder with the MZML files. And then, yeah, basically I have the same name, but just like with like that .mzml file name. And those are now, yeah, an open access format. So I can open them with like a bunch of like different like tools, both online as well as like local installations. So yeah, I think this is really a very nice way of yeah, like analyzing that data and making it public available. Okay, see, Tam has a question.
Yeah, a short one. Is there a reason why you use MZML files instead of MZXML?
So MZML is simply the newer version, and I think for like compatibility reasons, I would like stick to like the latest versions and yeah, choose like MZML. So GMPS and also MZ- also works with MZXML. So if you still have MZXML laying around, that's okay. But if you now convert new files, I would pick MZML as a format. All right. Okay, so now let me go back to the remote. Okay, so now, yeah, I have those files here. And now in the next step, what I want to show you is how I upload them to GMPS or massive repository. And now here, there's basically two ways. You can either use like the web interface to do that, or you can use an FTP client. So now for 3 files here, and let me check what file size. Yeah, it could be that we are already scratching the maximum of web-based uploads, so we may need to like use an FTP client. But we will see shortly if I now go here to massive.ucsd.edu, and then I'm gonna log in. And if you have not logged in there yet, you can quickly register on the top right, and it just like takes like a minute or so with your email and name. And then the same login you can also use later for GMPS, which we will cover in the next session. Successfully logged in now. And now, yeah, it's really just like a couple of clicks away. If I want to upload now here data, then I just go to submit your data on the bottom right here. Click that link. And then, yeah, it should basically open such like a ProteoSafe workflow where I can like put like different information in there, such as a title, but then also select the different files. All right, so it's still loading. All right, now we have it. So here I would give it like a meaningful title. So obviously this is the CMFI mass spec seminar test data. Okay, and then I can like provide like some general metadata information. So now the data I gave you is a mixture of different natural products. So no, I would just say the species is unknown for now. And you have to click add. Then the instrument was Q-exactive HF. Then there's no post-translational modifications that I know of. This is more something for proteomics data. Then I can like provide different like keywords, like, okay, this is a natural products. And it's LC MS. And then, yeah, I can, I don't know, define like a principal investigator. Well, in that case, could be myself here. Okay, and then I could also give like a short description. And yeah, basically like the more accurate you can like describe what you did here, the better it is for, I don't know, like future use of your data by either yourself in 5 years when you forgot already about it, or by others, obviously, that do not know your experimental design. And here it's just like, yeah, DDA, LC, MS, standards. Yeah, I think it needs like some minimum amount of characters. So let's add 4. Okay. So now if I have like all like this information here added, the next step would be that I actually need to select the files. And there's basically like one essential category, and this is like the peak list files. And when you hover over it, it actually tells you already, okay, this needs to be open format files such as like MZML, MZXML, or also like MGF. And then if I click on this, then it should open a new window, which now brings me to my personal user space. So here I can upload first data into like my personal user space. And then if I want to create a massive data set that is publicly available, then I can basically select files from like this personal user space. Okay, seems like internet is a little slow here today, but yeah, slowly it's loading. And yeah, basically what you can see here on the left are like, first of all, here on the top, different public data sets I already used, but then also here under my username, there's like different like private data sets I uploaded over the years. And yeah, you can say that there's you can see that there's quite some folders. But now for you, this should probably be all empty if you just created your account. So now, of course, like an important question is, how do you get your files now into your user space? And yeah, like the probably most simple way is if you go here to the top and change to this upload file button, then you should be able to drag and drop files here into like that field. But yeah, unfortunately, as I already thought here, when we read for like the details about the upload, is that, yeah, we typically need to have small files, 20 megabytes or less. And if we go to a folder here, we would see, all right, yeah, each of them is 60 megabytes actually. So we're probably not gonna get this uploaded through like this browser-based interface here. So yeah, this is being made a couple of years ago, and with like the newer machines now, we get more spectra and thus like way larger file sizes. Anyway, the good news is we can use an FTP client, although I originally did not want to show you that. I'm gonna give you a quick intro now in WinSCP. So this is like such like a file management software for basically connecting your local computer to a server. And what I can do here in like this interface is I can connect here to a new session, here to like my massive user space, and I have saved this here already. So basically you need to provide here the host name, FTP file protocol, and then your username, and then have to type in also your password when you click on login here. So it asks me to provide this. And then now I can basically use the software to also view all like the files in my personal user space here, but then also very conveniently just drag and drop files here into my user space. So you see, I just dragged and dropped it in here, and now on the bottom you can see, okay, it starts uploading. Okay, we got, oh yeah, 600 kilobytes per second, so not terribly slow, not super fast either. And yeah, probably gonna take like a minute or so till this is uploaded. All right. So now, yeah, I think to finish the task, I will just like pick a random other file, so to show you how to select it. But yeah, in your case, you can wait till yeah, you like uploaded it then later, and then actually like select your test files. So yeah, to do this again, I have to like select input files here, and then scroll down to whatever folder of interest, and then yeah, I think here I have some already. Oh, they're already appearing, although they're still, I think, uploading. So probably it's not going to work, but just as an example, I would basically like select here these 3 files, and then make sure that they're like kind of like blue highlighted, and then just go up and click on peak list files here. And then, yeah, it says add peak list files. And then what should happen is that now those 3 files should appear under the selected files list. And now if I say here, finish selection, they should basically appear here under peak list files. And now I'm good to go to submit this here to Massive. If this were proteomics data, I can also check here like proteomics exchange, and eventually like directly get like a proteomics change identifier. I need to put some some search engine files in there for that as well. That's not the case for metabolomics. Yeah, here we don't use that, and you can just make a data set with like the MZML files, for example. So then I would here click submit on the top, on the bottom right, and then now I should basically get here like a status thing, and it says running, and probably it's going to take a couple of minutes before it then has the data set created. One important thing is that creating a data set for now will first keep this in the private space. So once this data set is ready, there will be a particular button you would have to click in order to make your data public. So yeah, some people, especially when you like upload this for like a publication or so, then they often forget to make the data public. So yeah, till you click that button, it still remains private. All right, so I think with that, okay, let me close here the remote session. That was basically all I wanted to show you today. And now, okay, that leaves me just to basically tell you what we're going to do next time. So next time we're going to use that data we just uploaded, and then going to create like a first molecular network with that in GMPS. And yeah, I think with that, we're going to do questions now in a second. But yeah, for those of you who are taking off, thanks again for stopping by, and yeah, looking forward to move on with the molecular networks and also now with the discussions. So yeah, thanks.